Continuing. There's a typo on my version. Maybe you printed it off and there isn't a typo on your version anymore, but that is supposed to be the exact same equation as what we had before. So the value b is equal to the area under the curve of f of x squared plus 1. It says write down, and this is not the approximate, right? This is just the exact value. So this is no longer an approximate. So it says write down the definite integral. The definite integral is the only way to find the exact value. So the definite interval expression, interval from 1 to 3 of f of x, which is x squared plus 1, dx. You could write that out into this. You could take the integral, and that's 1/3 x cubed plus x, and we would have to evaluate that from 1 to 3. It does say to use your calculator to calculate this to 4 significant figures. So I will let you either practice plugging in and evaluating. Remember that you plug in 3 first. So that would be 27. 3 cubed is 27. A third of that would be 9, plus 3 would be 12. So you'd be 12 minus, and then you would subtract out what happens when you plug in 1. Or you can just use your integral values on your calculator. Either way, 4 significant figures would be 10.67. So the difference here, and this is, you'll notice it says, hey, find the percentage error of A relative to B, is that B is your exact area underneath the curve. The definite integral is the total area exactly of what's happening underneath the curve, beneath the curve, and above the x-axis. And A was an approximate of the area underneath the curve using the trapezoidal rule. And so we're like, okay, there's a difference. We can compare. The first one was 10.75, right? Our approximate was 10.75. And our exact that we found was 10.67. So, okay, percentage error. Remember that our percentage error formula, which is in our formula packet, is the approximate value minus the exact value, all divided by the exact value. And we do find the absolute value of that. And then we multiply it by 100 in order to turn it into a percent. Your approximate value is the one that is approximate, right? Your trapezoidal rule gives you an approximate value, 10.75. Your exact value is the one that is the definite integral. It is 100%, just that's what the area underneath that curve is. So that should be all enough information for you to be able to calculate the percentage area on your own. Plugging in the approximate, we get 10.75 minus 10.67, your exact, all divided by 10.67. Absolute value, and then multiply by 100, should give us, for 3 significant figures, 0.750%. I know sometimes when I multiply by 100 and it's still a decimal, I'm like, wait a minute, is that still a percent? Yeah, it's just a really, really small percent. Right? That is a very small percentage, which means that the approximating the area underneath the curve using the trapezoidal rule is a pretty solid way to approximate. Last question. So when we have a thing that we're trying to approximate the area underneath the curve. So for instance, we have a velocity versus time graph shown here. That's a train journey. Use the trapezoidal rule to calculate the total distance. So remember, going from velocity to distance. Remember, in order to get from distance to velocity, we had to find the derivative. So in order to go the other way, it's the integral, right? So moving from velocity to distance would be finding the integral of that situation. Since it's not a clear like equation, it's an irregular thing. And so we don't have like an equation that we could find the integral of then to be able to find the definite integral along a certain value and find the exact area. And so we would have to approximate it, or we would have to break it up into composite figures. We would need to use the trapezoidal rule. It doesn't really make sense here to like try and keep it consistently like a consistent interval in order to use our actual formula. And this is why. Is that if we kept it consistent, like let's say for instance every one, right? We would only have two trapezoids. That doesn't seem like a really good way. That would be this and then this. That's like not a very good way, just connecting first base to second base, first base to second base. That's not a really good way to approximate this. So, okay, maybe we wanted to split it into something that's slightly smaller. Maybe we wanted to go with every two. Well, that would be this, and then that would be this, and then that would be this, and then this, and then this. Slightly better, but we're still missing like quite a few of these area pieces. And so I would still say that we're pretty largely off by keeping it consistent like this. To break it down even smaller, I forgot my eraser, so we're just going to have to deal with that. To break it down into even smaller intervals, it would be every one. And then notice that going by every one interval, yes, we would get everything exactly, but then we're like starting to break up big chunks of area that like don't have to be separated into one. That is a rectangle. And so shouldn't we just find out what the area of that rectangle is and then add that in? So there are some times when using the trapezoidal rule that would be really helpful and really logical to do, very intuitive for that process. But sometimes when you've got something that's like, well, I could break it down to keep it a consistent interval in order to use the trapezoidal rule. I could break it down into some really small intervals to make it as like close as possible, or just create a composite figure and find the area of each of those pieces, right? So I would break down um, this total area into some smaller areas. So we've got this triangle, a rectangle, trapezoid, trapezoid, rectangle, triangle. I'll call it A1, A2, A3, A4, A5, A6. And so the total area there, which will be your distance because that's what the integral is. That's how the integral moves us from velocity to distance. Would just be the addition of all of those areas. And since it's a pretty straightforward large box situation, we can go ahead and do that. Just be aware that each of these boxes are 20 on the y-axis versus on the x-axis. Each of these boxes are 0.2, right? I think this guy is 1, so it's split into 5 sections on the x-axis, which means that 1 divided by 5 is 0.2, so each of those are 0.2. So the total area is A1, A2, A3, A4, A5, A6. A lot of work, maybe a little menial, but sometimes that's what we have to do. I'll go ahead and just work on this silently. I think you guys can handle it as well. Triangles versus rectangles versus trapezoids. So a bunch of different formulas. You could technically use the trapezoid formula for the area for both a triangle as well as a rectangle, right? So your first base for a triangle would be 0 and your second base would then be the height. So really what you're doing for adding the two bases, because you would be 1/2 times the height, which would be this distance, times base 1 plus base 2 would just be 0 plus, so you're really just multiplying by this dynamic, right? So your area of a triangle actually could be found using the area of a trapezoid. And same with your rectangle, is that you would be adding the same base twice. And so that's why multiplying it by 1/2 would then negate that. If you're adding the same thing twice and then multiplying it by 1/2 would get rid of one of them. So then you would just really be the height times the base. Kind of flipped, but just trying to keep that trapezoidal orientation going that we've established so far. So technically, you could use the trapezoidal equation for all of these because it would still work. But after that, you guys can finish the rest of this as I'm working on it silently. area of the triangle here, 0.5 times 0.2 is that base, 80 is the height, 0.4 would be the base here, 80 would be the height. Area of a trapezoid, 0.2 is the base, and then 80 is the first, well, 0.2 is the height, and then 80 would be the first base, and 60 would be the second base. Same with the second trapezoid, 60 and then 100 though for your bases. And then we've got this distance right here would be 0.6, and then the height of that guy is 100. And then for your last triangle, a half times 0.4 is this distance, and then 100 is that. So then we just need to go through and calculate that all, add it all together. Go ahead and do that on your own and tell me what you get. We end up getting exactly 150 kilometers. Now, here I'm not using an approximate because this isn't like an equation that we're trying to approximate the area under the curve. This is a shape that represents a velocity versus time comparison. And of this, we can find the exact area. And so that's why it is exactly 150. And that's it, the trapezoidal rule. It can be helpful and useful in certain situations, but in some situations, it's just better to use a composite figure and add up all those composite figures. It's up to you to determine which one is the correct one to use and when. Good job, guys.